My name is Syed Karishma and I am currently pursuing my Bachelor of Technology in Electronics and Communication Engineering at VVIT University. In today's seminar, I will be presenting on the topic of number system conversions, and let's get started about number system conversion. A number system is a way of representing numbers using different bases. The most common systems are decimal base 10, digits 0 to 9, binary base 2, digits 0 and 1, octal base 8, digits 0 to 7, hexadecimal base 16, digits 0 to 9 and A to F, and A's place is 11, B is 12, C is 13, D is 14, E is 15. Number system conversion means changing a number from one base to another. If we see decimals, other systems, divide the decimal numbers by, if we see here decimal to any radix. Decimal, divide the decimal number by the base and record reminders. Other systems in decimal, multiply each digit by base, power, position and add them up. And if we take binary to octal and hexadecimal, group binary digits, 3 bits for octal, 4 bits for hexadecimal, and convert directly. If we see here, the possible conversion of number system is as below. Decimal to any radix to decimal, binary to octal, hexadecimal, octal hexadecimal to binary. We again move to next slide. Now we discuss about decimal to any radix. For integer part, a successive division of a given decimal number by radix till coefficient becomes 0, and then note down all the reminders in reverse order. For example, if we take 52 base 10 to binary, in binary we only exist 0 or 1. 52 divided by 2, as we remainder is 0. 26 is divided by 2 is equals to 13, remainder is 0. 13 divided by 2 is equals to 6, remainder is 1. As well as the answer of 52 base 10 to binary is 110100. If we see for fractional part, successive multiplication of a given fractional part of the decimal number by radix or until the fractional part becomes 0, and then note down integer part in the normal order. In fractional part, a successive multiplication of a given fraction part of a decimal order by radix, or note down the integer part in the normal order. If you see here, one of the example, convert 0.74 base 10 to the binary. Base 10 to the binary, 0.74 into 2 is equals to 1.490, and we consider before the point number 1, and again we start multiplying the answer into 2, we get the answer. If we see here, the answer is 0.101111101. Okay, if we go for next slide. Now the concept of binary and octal hexadecimal codes. Binary code base 2. The definition for the binary code is a number system that uses only 2 digits 0 and 1. Each digit in the binary is a bit. Place value increases in power of 2 of 1, 2, 4, 8 and 16. Used directly by digital systems because hardware work within on state is 1 and off state is 0. Again, if we go for second one, octal code. For octal base is 8. Definition for the octal is a number system that uses 8 digits 0 to 7. Place value increases in the power of 8, 1, 8, 64 and 512 as well. If we see shortcut of binary, 2 power 3 is 8, 2 power n. Each group of 3 binary bits is equals to 1 octal digit. Usually for simplifying long binary streaks, these are the shortcuts for the binary. And if we see, here is the one example for octal. Again now hexadecimal. Hexadecimal code for base is 16. Hexadecimal definition of the hexadecimal: a number system with 16 symbols 0 to 9 and alphabets A to F, whereas A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. Place values are powers of 16. Very compact representation of a binary, since 4 binary bits is equals to 1 hexadecimal. If you see the example, convert the 11011 to the base 22 or B group in the 4 bits. If we divide it into 4 bits, if you see here 1101, we divide it from left to right. Okay, next, if we see now, image and representation of a binary, octal and hexadecimal code. If we see here binary, octal, wow, okay. Some example problems of binary, octal and hexadecimal codes. If you see here, some are the examples for binary, octadecimal and codes. If you see first one, convert the following, 41 base 10 converts into binary. Divide 41 repeatedly by 2. And at last, read reminders from bottom to top. In conversion of binary, we have to read the reminders from bottom to top. Okay, if you see here, we can see the octal rule recap. Integer part, keep dividing by 8, collect reminders from bottom to top. Fractional part, keep multiplying by 8, collect integer parts from top to bottom. If you see here integer part, there is divisor, coefficient and remainder in the form of octal digit. If we see the example for octal digit, 23 divided by 8, the coefficient is 15 and the remainder is 3. If we divide 15 divided by 8, coefficient is 1 and the remainder is 7. 1 divided by 8, coefficient is 0 and the remainder is 1. Reading the reminders bottom to top gives the answer 173. The fractional part, multiply by 8 repeatedly and record the integer part of each time. If you see here step current fraction, and the second column is third column step current function, and the second column is into 8 and third column is integer digit number fraction. We multiply it into 8, collecting the digits from top to down. In the above case, we take the reminders from bottom to top. In the fractional part, we are collecting the digits from top to down continuously. Okay, combine. And if we see here the note, 0.5989 is a non-terminating in the base 8. So the octal fraction repeats and stops after many digits are needed. And if you see the one of the example 123.589 from the above example, for this the note is 0.589 is a non-terminating in the base 8. So the octal fraction repeats and stops after as many digits as needed. At Next, the conclusion for the number system conversion, and I'm giving the conclusion for on my seminar topic. Number system conversion is an important concept in electronics and communication engineering as well as computer science. It helps us represent and process data in different forms such as binary from computers, octal and hexadecimal from the compact representation, and decimals for human understanding. By materializing conversation between these systems, we can easily understand how information is stored, transmitted, and processed in digital systems. This is a conclusion from my seminar topic, number system conversion. I have briefly explained all the concept. Thanking you.